We're very used to seeing the sun, I think, in beautifully, highly coloured images. And I was very affected when I first saw that film by Ruth and Joe, because it seemed to me a completely new aesthetic to go back to some of the original data. That was all data from the SOHO satellite, which was studying the sun. I'm going to introduce Dr. Lucie Green, who's going to pick up on that theme. So while we're switching over computers, I will do a short introduction of Lucie. Lucie is a solar researcher. She studies activity in the atmosphere of the sun. And she's based at Mullard Space Science Lab down in Surrey. Lucie has been very active as well as being a scientific researcher. She sits on a number of panels and scientific committees, but she's also been very active in public engagement with science. And when the BBC did their big stargazing week-long series, I think Lucie was very prominent in that one. And she's also a trustee of the Arts Catalyst, which is great. So she's been interested in the relationship between art and science and culture for a number of years. And what we try to do at Kosmica is mix a bit of art in with a bit of science, and with some with films and music. So, lovely. I'm going to hand it over to Lucie, and hopefully she's going to hit you with some hard solar science.
Do I need this? Okay. Well, thank you very much, Nicola, for the introduction. So my name's Lucie Green, and as you've heard, I work at UCL. And it's really nice to give a talk at an event where a film about the sun has been shown. And as I was sat watching the semiconductor film, I realised that what you've just done in the last 10 minutes is pretty much what I spend every single day doing. So I hope you have a nice feeling for what my job involves. So I work at UCL and I'm a space scientist, but I specialise in observational studies of the sun. And all the data that you just saw is exactly what I use in my research. And I recognise a lot of the events as well as events that I've studied and published on. But I work in a space lab, and really I have to mention the spacecraft that we use in our research, because without that we wouldn't be able to see the sun in the way that you've just experienced in the film. We've been studying the sun as long as humanity has existed, and we have fabulous records of things called sunspots on the surface of the sun that go back hundreds or a couple of thousand years. But having instruments in space high above the Earth's atmosphere means that we can see parts of the spectrum that are blocked by our atmosphere. So we can see the sun in visible light from the Earth, but once you go above the Earth's atmosphere, you have parts of the spectrum, such as ultraviolet light and X-rays, that the sun emits a lot of. And once you go above the Earth's atmosphere, you can see these kind of emissions from the sun. So I thought I would just show you some of the satellites that we have looking at the sun at the moment. So I've got a picture here, sun in the centre of the solar system, Earth in the orbit around it. The first satellite I want to mention is something called Hinaday, and this is a Japanese spacecraft that we launched in 2006, and it takes fantastic views of the sun. I'm going to show some of those images. I like to mention this one because even though it's a Japanese spacecraft, it carries a British telescope that was supplied and built by my department. And in fact, we have a really long relationship with the Japanese in doing space science. So recently I've been working with them looking at the next mission that we'll propose, that hopefully will launch about 2020. So all the time, as well as doing my research, we're interested in making sure we have telescopes to be able to do that research as well. So this is Hinaday, it's in orbit around the Earth. As well as looking at the sun from the perspective of the Earth, we've got two fantastic telescopes in orbit around the sun itself. And they're called the stereo satellites. Has anyone heard of the stereo satellites? I don't know, one person, yes, oh, fantastic. So this is a NASA mission composed of two satellites, but again, there's a British contribution to this. We always work internationally. And these satellites were launched in 2006 as well, but instead of being put into orbit around the Earth, we put them around the sun. And over time, they've moved away from us and have drifted apart. So both of them started off here at the Earth. One drifted off this way, and the other one drifted off that way. And so last year, for the first time in the history of the Earth, we were able to see the full 360-degree surface of the Sun. And we'll be able to do this for about the next 8 years, because these satellites are still on their way around the other, in orbit around the Sun. They'll cross, and then they'll head back in our direction again, which is fantastic. So as a solar scientist, I now know exactly what the Sun does every second of every day. And I'll have that for 8 years. Amazing. So then the stereo spacecraft. There's a few more in orbit around the Earth. This is a picture of Solar Dynamics Observatory, another NASA telescope. And this gives us the most spectacular images of the Sun. If you've been inspired by anything you've seen so far, please go onto the internet and look up Solar Dynamics Observatory. It's an incredibly powerful telescope. Well, in fact, there's a series of telescopes on board. We get 1.5 terabytes of data a day being sent down, all images of the Sun. We had to build a dedicated ground station to be able to get this data. It looks at the Sun 24/7 and gives us amazing views. And then the last telescope to mention, the last satellite, is SOHO. This is a joint NASA-ESA mission that was launched in 1995. It's been operating for years and still working, and this has really been the workhorse of solar physics, and I shall show you some data from there as well. And in the semiconductor movie, they had images taken by the SOHO satellite. They also used something called TRACE, which is another satellite still in orbit around the Earth, but no longer functional because it's been superseded by SDO. So my job is to study events like this, and some of these were shown in the film just now. This is a spectacular eruption with a rather tricky name to say. It's called a coronal mass ejection, to be careful about that. And I think they're absolutely fascinating as well as being beautiful. They look stunning. This is by far my favourite eruption from the surface of the Sun. And I'm going to come back to this and talk about it a bit more later. And in fact, when this event happened, it was in June last year, and a movie of it got sent around the internet. I didn't believe it was real because it was so spectacular. I thought someone had photoshopped these images. So I went back to the NASA data archive and made this movie myself just to convince myself that this huge and spectacular eruption really took place. I love the fact that you can see all this dark material falling down back to the Sun. A lot of it made it up into space, but a lot of it also fell back down. And where it falls back down, you see it impacts with the surface of the Sun, and these bright flashes where energy is released that heats up the gases appear. Absolutely stunning. And all the time there's this other feature quietly evolving away down in the bottom corner there. So these kind of images of the Sun are exactly what I use in my research. And they're only possible with space telescopes, because what we're looking at here is the Sun's light, part of the solar spectrum in the ultraviolet part of the spectrum. So this is it's not possible to see this light from the ground. It gets absorbed by the Earth's atmosphere. If we were able to see the Sun, or when we do look at the Sun from the ground, we see invisible light. And I can show you a picture of the Sun in visible light at exactly the same time as this. So these are images from the Solar Dynamics Observatory. So that it looks quite boring, which is why I don't do a lot of work with these kind of images. So what you can see is that there are dark spots on the surface of the Sun. These are the famous sunspots. Galileo observed these. We know that the number of sunspots on the Sun varies over time, rises and falls with a cycle of about 11 years. And at the moment, we are just coming out of a very long solar minimum. And we kind of thought that the Sun was switching off because these sunspots disappeared for a long time. But they came back, and now the number is on the rise, and we're due to have a maximum sometime next year. So this is the Sun in visible light. But what you can see is where the sunspots are in visible light, in ultraviolet, you have bright regions. And these regions are related. And I'm going to talk about that later on. So this is the Sun in ultraviolet light. We can go to shorter wavelengths of light and see how the Sun looks. And, I want you to notice how different the Sun looks, just between these two different parts of the spectrum. But if we go to even shorter wavelengths of light, the Sun looks totally different again. And this is another image taken from space at exactly the same time. So gone are the sunspots now, and instead what I hope you can make out are a series of loops. And that's what I kept seeing in the semiconductor movie, that the atmosphere of the Sun is full of loop structures. And they're the things that I think are really, really beautiful. I should probably say that the gases we're looking at here are incredibly hot. They have a temperature of 1,000,000 degrees and up. And because of that, the gases, the particles have been ripped apart. And so they're a sea of charged particles that we call plasma. And that's quite important in the evolution of the sun. Now, we've been looking at sunspots for hundreds and hundreds of years, but it was only just over 100 years ago that we finally found out what sunspots are. And that was because of an American astronomer called Hale. And he turned an instrument to the sun that was able to pick up the signature of magnetic fields. And so what we know today is that these arches, which sit, let me see, I'll point out, so here you can see some loops. So these loops that sit above the sunspot regions are actually a signature of magnetic fields in the sun's atmosphere. So everything that you were looking at in the movie was structure created by the presence of magnetic fields. So they start off at the surface of the sun and then they arch up high into the atmosphere as if you've got lots of magnets over the surface of the sun. And these magnetic fields completely dominate the solar atmosphere and lead to all the activity that you saw in the movies. So we can't study the sun without understanding magnetic fields. And just because I also like pretty pictures, this is a movie of the sun. The sun takes about 1 month to rotate fully. So you can see the edge of the sun here, and you can see how the atmosphere is full of changing dynamic arch-like structures, which are all magnetic field lines. And the hot gases in the atmosphere are trapped along the field lines, and they glow, and that enables us to see where they are. So we're not directly seeing the magnetic fields, we're seeing hot gases that are trapped along them. And you'll see that they change over time as well. There's also dark structures in here, something that erupts in this part of the screen. Huge amount of activity. So when we come back to looking at the eruption I showed you at the start, we can start to understand what's happening here. So this is an eruption of plasma, of gases, low down in the sun's atmosphere. But I want to make use of the fact that we see the sun across the electromagnetic spectrum with all the telescopes that we have now available. So this is the sun as it looks in ultraviolet light. This is the sun at exactly the same time, so it looks in visible light. So you can see the sunspots in the region where the eruption is taking place. And then this is a map of the magnetic field at the surface of the sun, so where the sunspots are. And we build telescopes that study the light coming from the sun, which leaves a fingerprint of the magnetic field in it. And we can use that to make these pictures. So what we have here in white are regions where we have a north magnetic field, or north pole. So imagine your bar magnet with your north and south poles. So white is where a north pole is, and black is where a south pole is. So white are where the field lines is a source of field lines and they come up into the atmosphere, and black is where they sink back down into the solar surface again. And this is really important information for people like myself. And we can use these maps of the magnetic field actually to build models in our computers of what's happening in the atmosphere above them, and we can start to understand what's driving these kind of eruptions. So using all these different data sets is really important for us. Now, in my movie previously, we looked at arch-like structures in the magnetic fields. And if you've ever had your bar magnet and sprinkled your iron filings over it, you'll remember at school that you get arch-like field lines emanating from one pole to the other. I'm interested in a slightly different shape of magnetic field, and that's shown by this eruption here. So this is another coronal mass ejection happening, taking gases with it out into space, and I'm going to try and stop it at a key point if I can. Am I going to be able to do this? So let me see, will I be able to stop it? Yes, great. So you can see that overall it's got an arch-like shape, but what I hope you can make out is that there's some kind of twist in the structure. I've kind of made a crude cartoon to illustrate this. Okay, I'm not an artist, but here we go. So what we have here, rather than nice arch-like magnetic field lines, is a bundle of field lines that have been twisted. So it's a bit like a rope or a slinky, and you've got twisted magnetic field lines. And most of the research I do is about looking for these very twisted structures of magnetic field. We very unimaginatively call them magnetic flux ropes, because they're twisted like a rope. And if you have these in the solar atmosphere, there's a whole range of interesting physics that goes with them. And it's quite easy to make them erupt upwards. So one of the big questions for these coronal mass ejections is, how does the material erupt up and away from the sun, considering that the sun has a really strong gravitational pull? But if we have a structure of a magnetic flux rope, you can keep twisting it up and twisting it up and twisting it up, and eventually this thing becomes unstable and up it will go. And they erupt with amazing velocities. The fastest one I've seen escape the sun at a speed of about 2,000 kilometers a second. And they carry the same mass as Mount Everest. I mean, they are vast. I haven't even given you a size scale here to show you how big they are. So the sun is as wide as 110 Earths lined up side by side. So these are big structures. They carry a vast amount of mass, and they go really, really fast. But we do understand pretty well how you can erupt these structures if they have a magnetic flux rope shape. So when it comes to sort of the building blocks in the solar atmosphere, you can have your magnetic loops, which is actually what the atmosphere is mostly composed of. But you can also have twisted structures. This is one of my favourite pictures as well. So here you can see how helical those field lines are because of the gases trapped along them. So the magnetic arches and the helical flux ropes are the two building blocks of the solar atmosphere. These structures are quite stable. These structures erupt into space. And actually, I've introduced another image here for you. So on the left-hand side, we've got our ultraviolet image of the sun. On the right-hand side, this is an artificial eclipse image. So you'll probably be familiar with the moon moving in front of the sun, blocking out the bright light, the visible light coming from the surface, allowing you to see the tenuous atmosphere of the sun. And we do this all the time with our telescopes. And this is an image taken with the SOHO satellite. This is the size of the sun here. This blue disk is our artificial moon, if you like, sitting in front of the sun. And then what we see is the faint structure in the atmosphere. And this is a coronal mass ejection in progress. One leg has actually detached from the sun, and one is still anchored there. And I just think it has beautiful helical field lines in it. So these are the kind of pretty pictures, as it were, of how the sun looks. I thought I would show you the kind of images that I produce in my research. So when we want to build up a model of a magnetic structure, we can do that in our computers. We can take the surface magnetic field of the sun, solve some equations, and then extrapolate and build up three-dimensional magnetic fields as a model. This is a similar thing that's been done in the US, and this is work done by Sarah Gibson. And what she's done is she's taken two magnetic polarities, a north pole and a south pole, and she's built a twisted flux rope between those two magnetic polarities. So the field comes out of one, is twisted around, and then sinks back into the other. And there's two different perspectives here. So you can see the twisted field lines, but also you can see at the edge of that bundle of field lines, the outermost field lines trace out this S-shaped structure. And then this is the same configuration but viewed from the side. So you can see field lines that come up and down underneath the structure and back up again. And there was a press release out a few years ago talking about these structures that was called S marks the spot, very cheesy. But these structures erupt very nicely to produce coronal mass ejections. And these are the kind of structures that I look at. These are the data sets that I use. So this is just a figure from one of my papers, and this is the surface magnetic field of the sun with the north polarity and the south polarity. And this is a matching image, but it's looking at the atmosphere sitting above that region. So again, we have to use our different telescopes to see different parts of the sun's atmosphere. And the right-hand side image is a picture of X-ray emission coming from the sun's really hot gases. And the loops that we see in X-ray that sit directly above this magnetic region have these S-shaped structures. So all my work at the moment is based around looking for these structures and measuring what the magnetic field is like in them, how twisted it is, how much magnetic field there is there, and then looking for that point at which the field can't be held down by the sun anymore and it erupts up into the solar system. This is a typical evolution that we'd see in an active region or in a sunspot region. So these are the structures sitting above the sunspots as the magnetic field comes up and then back down into the surface of the sun. And I've zoomed in just to one region. This is quite a small part of the sun. And you can see actually that the structure here is quite straight. It looks more like arcade field early on. But you can track these regions over time and they change, and you can see how the structure evolves until a day or so later when you have these S-shaped structures appear. And as soon as you see that, a few hours later, these things erupt into space. And coronal mass ejections are interesting from a scientific point of view. I mean, I want to know the physics of how they work, but they're also interesting from the point of view of how they affect us on the Earth as well. So it's the coronal mass ejections that they can go in any direction, but if they come towards the Earth, they are the events that impact the Earth's magnetic field, they shake it up, they energise it, which ultimately leads to the production of the aurora, the northern and southern lights, and also problems with our satellites. And even the effects come right down to the surface of the Earth, and they can cause problems with our electricity networks as well. So there's a big push at the moment to understand exactly what the magnetic field is like in these erupting magnetic flux ropes, so that when they get to the Earth, we can predict how intense the storm will be. And there's been loads and loads of stories in the news recently, particularly the Daily Mail loves to talk about this kind of stuff. And with solar maximum happening next year, there's been lots of stories about the sun wiping out life around the Earth as it destroys electricity networks because of these coronal mass ejections. That's not going to happen, but we still do monitor what the sun does on a day-to-day basis. So that's a bit about the research I've been spending most of my time on. Just to finish off, I wanted to talk about another kind of solar activity that I find really interesting and which is related to these coronal mass ejections. So I'm going to show another movie. This is a composite movie, so we've got an SDO image of the sun. Actually, let me run that again, because I want you to look out for a very faint ring of material. Oh, sorry. Let's go forward. So hopefully you'll see a ring of material, very faint, that moves out. And that was a coronal mass ejection that was directed towards us. And as it moved out and expanded, it formed a halo around the sun. And this is a zoom-in of the S-shaped region that produces an eruption. So this runs again. Hopefully you'll see the material coming out. We zoom in. This is the sunspot region with this overlying magnetic field, which had a flux rope shape, which erupted up. But interestingly, when we studied this event, we found that it produced something quite unusual, something that we call a sunquake. And it produced two of them. And I've got a movie. This is now a movie of the surface of the sun, so we've gone back down to the surface. And I hope you can just about make out ripples. It's very faint. Let me see if I can point them out. Ah, yes, here. So can you see? And this is zoomed into the surface of the sun now. You probably would get a few Earths lined up side by side across this image. But this eruption was so powerful that it generated an impact just below the surface of the sun that produced sound waves. And just like with an earthquake, those sound waves propagated out and they bent and came back up to the surface of the sun and produced a ripple. And as all of these waves moved out, they produced a series of ripples at the surface of the sun. So it looks like someone's dropped a stone in a pond, but it's actually something coming inside the sun that causes sound waves that come up, lift the surface, and make these ripples. And there's two sets of ripples here. So one has a source near here, and there's another source, even I struggle to see it on these movies, that comes out here. Maybe if someone can spot it, I'll buy them a beer later on. So when this eruption went off, it was so powerful that it delivered an impulse back into the solar interior and generated these beautiful sunquakes. And so at the moment, the work that I'm starting to look at is what's the physical mechanism behind the generation of these sunquakes. So the sun is visually beautiful, it's scientifically interesting. I mean, I find it completely fascinating. We have a huge range of telescopes looking at the sun now, and we make real progress in understanding what it gets up to. But of course, there's still a lot more to do. Each time we look at the sun, we see something new, like seeing these sunquakes, for example, and we want to understand how they're produced. So I think I've probably filled up my time. Thank you for your attention, and I'll hand back to Nicola, I think.
Well, we may keep Lucie a bit longer if there are any questions. We're expecting intelligent, perceptive, or incredibly naive and ignorant. Thank you. I'm going to pass a microphone around.
So I haven't got an intelligent question, but is it really, really loud?
Do you know, that's a really good question. I don't know.
Surely it wouldn't be. It's a bit in a vacuum there.
Yes, so we wouldn't be able to hear it, but the sun is full of sound waves, and we capture those. So you can work out the frequency of the sound waves from the ripples, from the rise and fall of the surface. And in fact, the whole surface, I mean, you can see the ripples really all over the surface of the sun, and detecting the ripples from the sunquake is quite difficult, because sound wave is a pressure pulse, it's a motion of material. And okay, as I speak, I'm moving the molecules in the air, but as the sun generates sound waves, it makes the plasma move, and at the surface you see these ripples. So I want to say that there is a lot of energy in these sound waves. And we compared them to earthquakes and found, you know, they're thousands of times more powerful than the earthquake we've ever had on the Earth. But, you know, these are big structures. The frequency would be very low. It's below our audible range. But yeah, I don't know how loud they would be if you were to put a speaker there. I have to go away and work that out now.
Marvellous. I think there was a question here.
Yeah. I had a totally insane idea when I was watching the semiconductor movie, which is, it felt like the sun was an intelligent being. The structures looked so complex and elaborate, it was hard to believe there was something just random going on. Have you got any measure of the kind of information content? I don't know how you express it.
Yeah, I mean, the relationship I have with the sun is like I know it personally. And so I can appreciate that, and it is hugely complex. These magnetic fields can be complex. A lot of the science behind it is very complex, but actually it's probably very typical for a star. And I think actually it might even be on the less complex side of stars, because I think the fact that we've been able to evolve next to this star means that it's probably quite calm. Yeah, I think the fact that the sun isn't, I mean, it is active and it is beautiful, but it is not that active in comparison to other stars. And also the fact that we have a magnetic field as well that protects us from a lot of this activity. Some of it breaks through, but most of it is deflected around our magnetic field. But magnetic fields are everywhere in the universe. And I often think it would be really nice to have, I don't know, magnetic eyes that could see all these fields. I mean, there's magnetic fields here, generated by the Earth, and then you go beyond the Earth's bubble, and you're in the magnetic fields of the sun, and then you go beyond that bubble and you're in the magnetic fields between the stars. So they're everywhere, and because everything's moving, it's able to move the magnetic fields and twist them up, which ultimately is what can produce these structures.
Another question? Oh, one at the front.
Thanks very much for your talk. I just had a couple of questions about the ripples. So these ones are the sunquake ripples, and then are you suggesting that there are constant ripples that are made just by internal sound, and is that the shimmering surface, or is that something else, or do these ripples look different?
Yeah, there's all kinds of ripples. So my colleague has processed these images to bring out the sunquake ripples, but actually the gases in the sun are constantly moving, so the heat that's made in the centre of the sun means that you have big packets of gases that get heated and rise up and then cool and then fall down again. So we often talk about bubbles in a pan coming to the top and then disappearing, and more gets heated and they come up again. So the surface of the sun is constantly in turmoil, and those motions we think generate lots of sound waves. And so the sun is a big bell. It's constantly oscillating, and lots and lots of different kinds of sound waves, frequencies of sound waves all over the place, that you would then have to process the data and pick out the ones that you wanted to study.
Great, thank you.
Question at the back.
Hello, Lucie, it's Rob Lafreniere, curator here. Just a question about solar events and its effects on Earth systems. Solar events and space weather in general. What's the sort of greatest event that's happened so far that's affected electronic and communication systems on the Earth, and what are we likely to expect in the future on that line?
You know, that is the question we're all asking. So the biggest solar event, or the biggest event from the sun, or no, let me rephrase that. The event from the sun that had the biggest impact is an event that happened in 1859, and it's called the Carrington event because it was a brewer called Richard Carrington who just happened to be observing the sun. I mean, the sexy solar science in 1859 was to draw these sunspots and just count them, draw them, what did they look like? And he was making his drawings, and he suddenly saw a flash of light that no one had ever seen before on the sun. And so he drew it down, and then he ran off to tell somebody else, and by the time he came back, the bright patch in the sunspots had gone. But 18 hours later, on the Earth, huge displays of the aurora were produced, and the aurora normally are seen in ovals quite close to the poles. But when a really strong solar storm hits us, they move down towards the equator. And in this event in 1859, they were almost seen at the equator. The effect was that strong. But these events affect our technology more than anything else. And in those days, they didn't really have anything. It was pretty much just, well, it was just the telegraph. But the telegraph wires had currents created along them, ultimately because of changes in the Earth's magnetic field. And magnetic fields and currents are sort of intimately related. So if you disturb the Earth's magnetic field, you induce currents. And these currents flowed along the telegraph wires, so they could turn off the batteries to send their messages. There were fires as charges, as sparks happen, as charges discharge themselves. And it was a huge storm. When these events happen nowadays, we see many more effects, but the storms themselves have been a lot smaller. There was a big storm in 1989 that took out part of the Canadian national grid, and 6 million people lost their electricity when that happened. So we do monitor the sun all the time, and in fact next week I'm in the US for a meeting exactly discussing this. I'm not sure which would be the biggest solar storm that's happened recently. It's quite hard to get that kind of information because a lot of satellites get affected.
There was one for the tsunami, the Japanese tsunami. The Institute of Electrical, IEC, had a talk by a chap who came over from NASA.
Aha.
But he was only concerned about the communication.
Yes.
Disruptions to communication. And he gave the lecture and he said, I've just prized myself away from the screen, from his computer, but some enormous solar flares had occurred. And then the tsunami happened the following day.
Yeah, we don't think there's any link between solar activity and tsunamis, though. People have speculated about it. Yeah, I know. It's difficult, isn't it? Because you think, oh, is it coincidence? Is it correlation? Was it causality? But yeah, nothing that we know of. So the sun definitely affects our magnetic field, but I'm not sure it can affect tectonics like that. But yes, they do have massive effects. And what I could say is that there was a big study in the US that looked at the cost of a repeat of the 1859 event, and taking into account it would affect our satellites, which means our time stamps, or our banking, communications, TV, effects on our electricity networks, if we lost any power lines that we rely on for refrigeration, blah, blah, everything is, this infrastructure is kind of at the base of everything. And so they think that the cost would be in excess of $2 trillion US, which is just mind-blowing. So there's a lot of work going on to put the solar science that we do into practice to protect these systems. And in fact, in the UK, the government put the so-called space weather on the National Risk Register in March this year. So even in Britain, a tiny little country that's not really in the right, well, we thought in the right place to be susceptible to the sun, so we think it's more underneath these auroral ovals. Even we're thinking about it, because ultimately we're so globally connected now, if systems go down, we feel the impact.
We're more affected by the jet stream in most countries.
Yeah.
The jet stream has been affected by the solar flare.
That's a good point. You probably can't hear what's being said, but so the gentleman's made the point that we're very affected by the jet stream in this country. And yes, there's some work being done by Mike Lockwood at Reading University, who thinks that this very long solar minimum we had, so the sunspots disappeared, we had very few coronal mass ejections, very few flares, and he's wondering if this decline in solar activity could affect the jet stream, which then affects our climate. It's proposed.
Piers Corkins can't.
Oh, Piers Corkins. Yes, I know him. That's a different set of work, yeah. We can talk afterwards about that.
Wonderful. There's a question from the back.
Thank you. Hi. I am curious to know if there is a central point of debate or focal challenge that you as a scientist within this observational mode of study have to deal with as compared with other types of sciences that can materially engage with their subjects, so either philosophically or technically, because you have to rely on photography and can't actually touch and work with what you study, if there's something that your department faces in either of those realms.
Actually, I realised I had one more slide after this, that maybe, because you were saying we can't touch the sun, and you're absolutely right. It would be the ultimate thing to get to the sun and get to the surface and be able to measure what it's like there. It would be a brutally harsh environment to do that. But we do have a mission that's kind of going most of the way there, and we're going to launch it in 2017. It's called Solar Orbiter. And so this is just an animation showing the sun at the centre of the solar system, Earth and Venus in orbit around the sun, and the Solar Orbiter spacecraft. It's the kind of blob without, which one is it? Yes, this one here. Yes, that's right. So the Solar Orbiter spacecraft is a European mission. My colleagues are building telescopes that will fly on it, and it will go really close to the sun, so within the orbit of Mercury, which means we'll be getting right into the sun's atmosphere, sensing all these outflows just after they've left the sun. And this is going to be an amazing, amazing satellite. And it gives us a different perspective on the sun, literally, because it is in an orbit that's inclined relative to our orbit and the view that we normally have of the sun. So that, for me, is us being able to get up close and sort of taste and smell what's coming off the sun.
Wonderful. Are there any other questions? Oh. Okay.
I'm curious. Is there, the sun activity that affects the distance or the gravity between Earth and Sun? I don't the rotation, the orbit. Can the other planets go far or come close because of continuous activities with the sun?
So the solar activity, especially these coronal mass ejections that carry large amounts of mass, they sound massive to us, but they're just a tiny, tiny fraction of the overall mass of the sun. So it doesn't affect us at all in terms of the gravitational interaction. They're just too small. In theory, a huge eruption could, but what we see happening is just too small, so they wash over us and our orbits don't change, luckily.
Okay, I think we're going to take a break now, so let's give a big thank you to Lucie.